Thanks for joining us as we walk through our bank queue simulation. To help explain the architecture, we will split the solution into smaller, easily digestible sections. First, the dynamic queue, then the priority scheduling structure, the impact of multiple tellers, the events that drive the simulation, and finally, customer abandonment along with its impact on the statistics. This project is a bank queue simulation web application that dynamically visualizes and manages customer queues and teller activities in a bank. It features real-time updates of statistics like queue lengths, wait times, and abandonment rates, along with visual representations of customer queues and teller statuses. The simulation logic is implemented in JavaScript, with modular components for customers, tellers, and queues, and the UI is built using HTML and CSS for an interactive experience. This is a model of a real-world bank environment, where customers arrive at different times and have different needs. The idea is to understand how the queue behaves, how long people wait, and how efficiently tellers are used. In our system, customers are grouped into 3 types: regular walk-ins, people with appointments, and those who need priority service. We've designed the simulation so that appointment and priority customers get served first. This reflects how real banks often try to improve service for high-need or pre-scheduled clients. Now, as customers arrive, they're placed into the appropriate queue. Tellers are either idle or busy. The system continuously checks which teller is free and assigns them the next eligible customer based on priority. If a teller is available and there's a waiting customer, service begins immediately. What makes the simulation dynamic is the way it handles queue switching and abandonment. If a queue is too long or moving slowly, the system might shift a customer to a shorter or faster-moving line. And if customers wait too long without being served, they can leave. That's recorded as abandonment, and it's an important metric to track. Throughout the simulation, you'll see a visual representation of the queues and teller activity. Behind the scenes, we're constantly updating statistics like average wait times, queue lengths, and how many customers leave before being helped. These metrics give us insight into where the system might be failing and what can be improved. There's also an interface that lets users control the simulation. You can pause it, restart it, or change the number of tellers, and adjust customer arrival rates. This makes it easy to experiment with different strategies and see how they affect performance. As you watch the live demonstration, pay attention to how the system reacts. The dynamic queue logic processes inputs and generates outputs to reflect real-time queue and teller activity. The inputs include queue data such as the type of queue, its length and average wait time, as well as teller data, including their status, type, and the customer they are serving. Additionally, simulation time and statistics, like average queue length, wait times, abandonment rates, and customer satisfaction, are also inputs. The outputs are dynamically updated and displayed in the user interface. These include a visual representation of queues, categorized by type, such as appointment, priority, or regular teller queues, showing their length and wait times. Tellers are also displayed with their status, indicating whether they are busy or idle, and the type of customer they are serving if applicable. The statistics panel updates in real time, showing metrics like average queue length, wait times, abandonment rates, and customer satisfaction. This logic ensures the interface provides a clear and accurate real-time view of the bank's operations. The queue logic dynamically manages customer flow by categorizing queues into types: appointment, priority, and regular. Each queue tracks its length, average wait time, and associated teller. Special queues are displayed first, followed by regular queues, which are grouped by teller type and ID. Customers in each queue are represented visually, providing a clear view of queue status. The priority scheduling logic ensures that customers in special queues, such as appointment or priority queues, are served before those in regular queues. The simulation identifies these queues by their type and processes them first. This prioritization ensures that high-priority customers experience reduced wait times, improving overall satisfaction for these groups. Queue switching occurs when a customer moves from one queue to another, typically to optimize wait times or balance teller workloads. The simulation tracks these switches and updates the statistics panel with the total number of switches. This logic ensures efficient resource utilization and minimizes customer wait times by redistributing the load dynamically. Customer abandonment occurs when a customer leaves the queue before being served due to excessive wait times or dissatisfaction. In the simulation, this is tracked as an event where a customer exits the queue without reaching a teller. The abandonment rate is calculated and displayed in the statistics panel, helping to measure the efficiency of the queue system and identify bottlenecks. The teller logic in the simulation is responsible for managing how tellers interact with customers and handle queues. Here's a detailed breakdown. Each teller is assigned a type such as regular or priority, which determines the type of customers they can serve. For example, a priority teller may also handle customers from the priority queue, while a regular teller serves customers only from the regular queue. Tellers can either be busy or idle. When a teller is busy, they are actively serving a customer, and their status reflects the type of customer they are handling. When idle, they are available to serve the next customer in the queue. When a teller becomes idle, the logic assigns the next customer from the appropriate queue. This assignment is based on priority scheduling, ensuring that customers in higher priority queues are served first. In summary, the simulation operates through a series of events that dynamically update the state of queues, tellers, and statistics in real time. Here's an overview of the logical flow. Throughout the simulation, the customer arrival event periodically adds new customers to the appropriate queue, whether appointment, priority, or regular. When a teller becomes available, the teller assignment event assigns the next customer from the queue based on priority scheduling. The queue update event continuously refreshes the state of the queues, including their lengths, wait times, and visual representation in the interface. The statistics update event periodically recalculates and updates key metrics such as average queue length, wait times, abandonment rates, and customer satisfaction. If a customer is moved between queues to optimize wait times or balance workloads, the queue switching event is triggered. Finally, the customer departure event occurs when a customer is either served or abandons the queue, updating the queue length and statistics accordingly. This sequence of events ensures the simulation runs smoothly, providing real-time insights into queue dynamics and teller performance.